In ammonia, that is NH3, one hydrogen atom is replaced by an hydroxyl group which is called as hydroxylamine. If the oligosaccharide is undergoing hydrolysis and forming two monosaccharides, then it is called as a disaccharide. You have an aldehyde on the top, you have hydrogen here, hydroxyl here, and an alcohol here. So this is an asymmetric carbon atom. Asymmetric means all the four substituents attached to it are different. Hello everyone, this is Ambli Unnikrishnan from the Department of Chemistry. So today I am back with the next chapter of your syllabus, which is the last one, that is biomolecules. Okay, so what are biomolecules? It's actually a branch of chemistry which is called as biochemistry, wherein we'll be studying in biomolecules about those different biomolecules which are necessary for the survival of human beings, right? For example, vitamins, hormones, DNA, RNA, that is the nucleic acids, right? Regarding carbohydrates, the different types of proteins, all of that we are going to discuss in this chapter. So this is quite related to biology as well, which you have studied in your first level, that is class 11 as well, regarding the biology part of it also. So this is under the branch biochemistry, where we are going to study quite related to biology as well. So the chapter name is biomolecules. So in today's session, we are going to see the introduction to carbohydrates. We are going to start with carbohydrates and the classification of carbohydrates, preparation of glucose and the structure of glucose. So you might be familiar with these words, carbohydrates, glucose, right? All of these are important for the human survival. Right. So let's begin with carbohydrates. So what are carbohydrates? They may be defined as optically active. Now what is optically active? Which has the capability to rotate plane polarized light towards the clockwise direction or anti-clockwise direction. So we have already studied about polarity, that is optical activity, all of that in the previous chapters itself, right? So they are optically active. So what is the first point that you can understand about carbohydrates? They are optically active. They have the capability to rotate the plane polarized light towards the right or left, right? Polyhydroxy aldehydes or ketones. So they are optically active polyhydroxy. Now what does polyhydroxy means? Hydroxy means the OH group, right? So polyhydroxy means it has having more than one hydroxyl group, that is OH group. So it is having more than one hydroxyl group of aldehydes or ketones. So it is having the functional group aldehyde, or it can be a ketone, or also the compounds which produce such units on hydrolysis. So either carbohydrates are those substances which are optically active polyhydroxy aldehydes or ketones, or those substances which on hydrolysis gives these polyhydroxy aldehydes or ketones. They are called as carbohydrates, right? Carbohydrates are also called as saccharide, which in Greek comes from the word saccharon, which means sugar. Okay, so this is the general introduction about carbohydrates. So they are optically active polyhydroxy aldehydes or ketone. So in detail we are going to study about this. So let's see how carbohydrates are classified into. So carbohydrates majorly it is classified into monosaccharides. Saccharides, we know it's the another name for carbohydrates itself. So monosaccharides, oligosaccharides and polysaccharides majorly classified into these three. So from the name itself you can say monosaccharide, which means only one unit will be there. Now what is this monosaccharide? So in detail we are going to see about all this in the next upcoming slides. So monosaccharides, oligosaccharides. Oligo means it will come around 2 to 10. Now what is this 2 to 10? We are going to see now. And the next one is polysaccharide, means many units will be there. Now oligosaccharides are further classified into disaccharides, trisaccharides and tetrasaccharides. So from here itself you can see di stands for 2, tri stands for 3, tetra stands for 4, right? So this is how they are being classified into, that is monosaccharides, oligosaccharides and polysaccharides, wherein oligosaccharides are further classified into di, tri and tetrasaccharides. So let's see. The first one is monosaccharides. So the monosaccharides are polyhydroxyaldehyde or ketones which cannot be hydrolyzed to give simpler carbohydrate. So monosaccharide means only one unit will be there, and that cannot be further hydrolyzed to form any polyhydroxyaldehyde or ketone. So it won't undergo any further hydrolysis to form further units. So that is a basic unit there which forms a carbohydrate. So that is called as a monosaccharide. Only one saccharide unit will be there. So the example for these are glucose, fructose, ribose, etc. All these under hydrolysis do not give any further smaller units. Okay. So monosaccharide is the smallest unit of the carbohydrate. Moving on to the next one, that is oligosaccharides. So carbohydrate which gives 2 to 10 monosaccharides units on hydrolysis are called as oligosaccharides. So oligosaccharides are having 2 to 10 monosaccharide units. So oligosaccharides, when it undergoes hydrolysis, it will split into this 2 or more than 2. It can be either 2 monosaccharides it will give, or up to 10 monosaccharide units also it can give. So around 2 to 10 monosaccharides will combine together to form an oligosaccharide. That is why oligosaccharide on hydrolysis will give 2 to 10 monosaccharide units. They are further classified as disaccharides, trisaccharides or tetrasaccharide depending upon the number of monosaccharide units they provide on hydrolysis. If the oligosaccharide is undergoing hydrolysis and forming 2 monosaccharides, then it is called as a disaccharide. If it produces 3 monosaccharides, it is called tri. And if it undergoes hydrolysis and forms 4 units of monosaccharides, it's called as tetrasaccharide. Right. Now example is sucrose, lactose, maltose. Now the sucrose, lactose, maltose, all these are examples of disaccharide. They will hydrolyze to form 2 monosaccharides units. Now which are those units we are going to study in detail in the upcoming sessions, right? Now polysaccharide, carbohydrates which yield a large number of monosaccharides, okay? That is more than 10 monosaccharide units will be formed when it undergoes hydrolysis. Right, and examples are starch, cellulose, glycogen, gums, etc. Polysaccharides are not sweet in taste. Okay, polysaccharides, they are not sweet in taste, hence they are also called as non-sugars. Just now we discussed in the beginning that carbohydrates are called as sugars because they generally have a sweet taste. But considering polysaccharide, that means which is made up of a more than 10 monosaccharide units, they are not sweet in taste, hence they are called as non-sugars. Okay, carbohydrates are called as sugars, but polysaccharides are not called as sugars because they have a large number of monosaccharide units which loses its sweet taste and it's called as non-sugar. Right, now what are sugars and non-sugars? Let's see. Sugars are crystalline solids soluble in water and sweet to taste. So they will be soluble in water, sweet to taste. Example, glucose, fructose, etc. All these are sweet in taste, hence they are called as sugars. Now non-sugars are amorphous. They are amorphous, insoluble in water and tasteless. They do not have a sweet taste. Right. Example, starch, glycogen. See, starch and glycogen, the examples itself, they are polysaccharides. So they don't have a sweet taste. They are non-sugars. Right. Now sugars may be further classified as reducing sugar and non-reducing sugar. Now what is reducing sugar? These are those which reduce Felling's or Tollens reagent. They have free aldehydic or ketonic group. Okay, they have free aldehyde or ketone group because of which it can undergo reduction under the presence of Felling's or Tollens reagent. So in aldehydes, ketones and carboxylic acid chapter, we have studied the test to distinguish aldehydes and ketones, that is Felling's test and Tollens test. In detail, we have discussed it there. So there we have studied the aldehyde group will show the Felling's test or Tollens test. So that in detail we have studied there. So as of now, reducing sugars are those the ones which will show that test towards Felling's test or Tollens test. Clear? Now, non-reducing sugar are those which do not reduce Felling's or Tollens reagent because they do not have a free functional group. Example is sucrose. So, what does this free functional group means? It should have an open free functional group so that it will be able to reduce, right? That means that aldehyde should be present as it is so that it can undergo reduction under Felling's or Tollens reagent. So, reducing sugars are the ones in which the aldehyde group is not free. Clear? Now, moving on to the preparation of glucose. So, first we are going to start with glucose. We are going to study the preparation and the structure of glucose in detail. Okay. So, the first one is from sucrose, or it is also called as cane sugar. Right, the first method is from sucrose. If sucrose is boiled with dilute HCl or H2SO4 in alcoholic solution, glucose and fructose are obtained in equal amounts. So, glucose and fructose are obtained when sucrose is being boiled in presence of an acid, right? So, C12H22O11 is sucrose, right? It is boiled in presence of an acid. Okay, what you are going to get? C6H12O6 and C6H12O6. Both have the same molecular formula, that is glucose and fructose. So, this is an example. Sucrose is an example of a disaccharide, right? It underwent hydrolysis and formed two monosaccharide units. One is glucose and fructose. So, this is a method of preparation of glucose. So, from which you can obtain glucose, right? The next one is from starch. So, commercially glucose is obtained from this method. Glucose is obtained by the hydrolysis of starch by boiling it with dilute sulfuric acid at 393 Kelvin under pressure. So, C6H10O5 N times. Okay, this is a big polysaccharide unit and N moles of water. Right, we are boiling it in presence of an acidic medium. What you are going to get? NC6H12O6. So, here also you are getting glucose. So, starch can undergo hydrolysis and form glucose, or else sucrose can also undergo hydrolysis and form glucose and fructose. Clear? So, these are the two methods of preparation of glucose. Moving on to the structure of glucose, which is very important. So, we understood the molecular formula of glucose is C6H12O6. So, from that basic things what we can understand is that in glucose there will be 6 carbon atoms, right? So, the molecular formula is clear, that is C6H12O6, but what is the structure of glucose was not clear. How exactly the carbon atoms are arranged was not clear. So, there were various different reactions which helped in the understanding of the structure of glucose. So, one by one we are going to study different reactions and different experiments which was done, so that we were able to conclude different results based on the structure of the glucose. So, let's see. Glucose is an aldohexose. Now, what does this mean? Aldo stands for aldehyde. That means glucose is having an aldehyde group and it is also known as dextro. So, this aldo stands for, it is having an aldehyde group. Hexose. Now, what does this hex stands for? Hex stands for 6 carbon atoms. So, two things we understood from here. Glucose is having 6 carbon atoms and also it is having an aldehyde group. So, it is a aldohexose. Also, it is also known as dextrose. Now, what is this dextrose? Dextrose stands for dextrorotatory. Already we have discussed, this is optically active. So, it is having the ability to rotate the plane polarized light. So, it will be rotating it towards the right. That is why it is called as dextrorotatory or else dextrose. Clear? So, its molecular formula was found to be C6H12O6. So, now as discussed, we are going to see the various reactions with various reagents so that we were able to conclude the structure of the glucose. First one, on prolonged heating with hydrogen iodide, it forms normal hexane, suggesting that all the 6 carbon atoms are linked in a straight chain. Okay, so this is the glucose which is shown here, which is having 6 carbon atoms. So you can see 1 here, then you have 4 here and 1 here. So total 6 carbon atoms are present. Okay, and then you have the aldehyde, CHO is present here, and you have an alcohol here, CH2OH. So this structure we are going to discuss in detail. So when glucose, as of now we do not know the structure of glucose. So when glucose was taken and it was made to react with hydrogen iodide, we got a straight line structure. That is, a straight chain hexane was formed. CH3, CH2, 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 CH3. This is normal hexane. So what does that indicate? That means all the 6 carbon atoms in glucose are present in a straight chain. Okay, that was the first result that we found regarding the structure of glucose. So, there are no other branches regarding the carbon atoms. All the 6 carbon atoms, that is 1, 2, 3, 4, 5, 6. All the 6 carbon atoms are present in the straight chain. Okay, so that was the first thing. Now, glucose reacts with hydroxylamine. Hydroxylamine is NH2OH. We have studied this as a derivative of ammonia, right? In ammonia, that is NH3, one hydrogen atom is replaced by an hydroxyl group which is called as hydroxylamine. So, glucose will react with hydroxylamine to form an oxime. oxime and adds a molecule of hydrogen cyanide to give cyanohydride. This reactions confirms the presence of carbonyl group. Okay, so you can see here, this is your glucose. It reacts with hydroxylamine and forms an oxime. So if it is forming an oxime when it is reacting with hydroxylamine, confirms that there is a carbonyl group present here. Which is the carbonyl group? Aldehyde is present here, right? As of now, we don't know. We are coming on to the structure. Okay, so you can see here the CHO which is written here, it is C double bond O H, right? And you have CHOH 4 times and you have CH2OH. So what did we confirm now? Because when it is reacting with hydroxylamine, it is forming an oxime. So that is because of the presence of this double bond O here. So instead of this oxygen, NOH will be substituted. So this double bond will remain here, NOH will be substituted in place of the oxygen atom. So you are getting an oxime there. I hope it is clear. Same way, when it is going to react with HCN, you are going to get cyanohydride. So from these two reactions, it was confirmed that there is a carbonyl group present. That is, this C double bond O is there in this particular glucose structure was clear, right? But we know that it's a carbonyl group. Whether it is aldehyde or ketone or carboxylic acid, which one it is, was not confirmed. So two things, I hope it is clear. That 6 carbon atoms are arranged in a straight chain was clear for you. The next reaction gave us the idea that there is a carbonyl group which is present, because of which oxime or cyanohydrin is formed, right? Now we are going to find which exactly is that functional group which is containing the carbonyl group. So let's see. Glucose gets oxidized to 6 carbon carboxylic acid, which is called as gluconic acid, on reaction with a mild oxidizing agent like bromine water. This indicates that the carbonyl group which is present is an aldehydic group. Okay, so we know that aldehyde undergo oxidation under the presence of mild oxidizing agent to form carboxylic acid. We have studied this in aldehydes, ketones and carboxylic acid chapter, that aldehydes undergo oxidation to form carboxylic acid. So when glucose was taken and added bromine water, we got gluconic acid. That means this aldehyde got converted into carboxylic acid. So as we are getting glucosic acid, we got to know that yes, it is getting converted into carboxylic acid. So if it is getting converted into carboxylic acid, means that what should be present there, which will be the carbonyl group which is present there, it must be an aldehyde, right? Only aldehyde can convert or oxidize into carboxylic acid under the presence of bromine water. That's a mild oxidizing agent. So it was confirmed that it is going to be an aldehyde, right? Next one, acetylation of glucose with acetic anhydride gives glucose pentaacetate, which confirms the presence of 5 hydroxyl groups. Since it exists as a stable compound, 5 hydroxyl groups should be attached to different carbon atoms. So glucose, again, when it was made to react with acetic anhydride, that is CH3CO, CH3COO. So this is called as acetic anhydride. So when it was made to react with acetic anhydride, we got glucose pentaacetate. So this was the structure you are getting. So the anhydride part was added up there. So the hydrogen here was replaced by the COCH3 part here. So 4 times. And you have one more hydroxyl group here, in which the hydrogen was replaced by another COCH3 group. So you got an acetic anhydride was added, and which will give you glucose pentaacetate. So if it is forming glucose pentaacetate, means that there must be 5 hydroxyl groups which is present, right? So it means that 5 hydroxyl groups should be present, then only the hydrogen can be replaced by an anhydride group there, that is COCH3. Clear? So now from that we got to know that this pentaacetate group which is being formed, it is very stable. So from that it means that all of these hydroxyl groups, that means the 5 hydroxyl groups are present in 5 different carbon atoms. It is not present in the same carbon atom. Okay, so clear? So all the 6 carbon atoms are present in straight chain. Then there is a carbonyl group, and the carbonyl group is an aldehyde. And now we got to know that there are 5 hydroxyl group, and all these OH groups are present in different carbon atoms. Now moving on to the next one, oxidation with nitric acid. What is happening? Glucose as well as gluconic acid both yield a dicarboxylic acid which is called as saccharic acid. This indicates the presence of a primary alcohol. Okay, so there is also a presence of primary alcohol here, because of which even if gluconic acid, this is gluconic acid, right, and this is glucose, both of them will undergo oxidation to form saccharic acid. So as you can see here, you have a COOH here, that is carboxylic group, and you have primary alcohol here. This is called as gluconic acid. So when this is undergoing oxidation, see, you are getting a COOH here as well. And now here also you can see there is a primary alcohol group here and aldehyde here, and this undergoes oxidation to form COOH on both the sides. So what does that mean? It is undergoing oxidation to form the carboxylic acid here, which is the saccharic acid. So it means that there is a primary alcohol also present, okay, which is present on the first carbon atom, which we will be discussing. So I hope this is clear. All of this were the results that were formed during the understanding of the structure of glucose. So from which we finally understood the structure of glucose, that is the exact spatial arrangement of different OH groups was given by Fischer. So the structure was given by Fischer after studying many other properties, and it is represented as follows. So let's see. There are 6 carbon atoms. That was the first thing. So you have 1, and this junction is the second one, third one, fourth one, fifth one, and the sixth one. All the 6 carbon atoms are present in the straight chain, right? And which is the functional group you are having, which is the carbonyl group? It is aldehyde. You have the carbonyl group, which is aldehyde. Then you have 5 hydroxyl groups. You are having 1, 2, 3, 4 and 5. That is also okay. Now what else you are having? A primary alcohol also you are getting. So this is the structure of glucose. So now you can see all the 6 carbon atoms are written here, and the hydroxyl group, this is present on the second carbon atom, this in the third, fourth, fifth and sixth, right? But you can see in the second carbon atom, fourth carbon atom and the fifth carbon atom, the hydroxyl group is written on the right side. But on the third carbon atom, it is written on the left side. So this is the structure of glucose. Now why it is like that and how you can differentiate which structure exactly is this, let's understand, right? So glucose is correctly named as D plus glucose. So it's not just written glucose, it is written as or mentioned as D plus glucose. Now, what does this D stands for? This D doesn't stand for dextrorotatory or levorotatory. Don't get confused with that. This D is based on the presence of this hydroxyl group of the first carbon atom. So, let's see how that is done. And that plus stands for whether it is dextro or levorotatory. So, while beginning with glucose itself, we have discussed that it is a dextrose. That means the plane polarized light is rotated towards the right. So, this is dextrorotatory. So, the plus stands for dextrorotatory. And what does this D stands for? Let's see. The D represents the configuration, plus represents the dextrorotatory nature of the molecule. And it may be remembered that D and L have no relation with the optical activity. Okay. So, the capital D and L are not the signs which help you to identify whether it is dextro or levo. It is just the configuration. And plus and minus give you dextro or levo. So, now let's see about D and L. Right, the letters D or L before the name of any compound refers to their relationship with the particular isomer of glyceraldehyde. Glyceraldehyde contains one asymmetric carbon atom and exists in 2 enantiomeric forms as shown below. Okay. So, how you can identify whether it is D or L? So, for that you have to consider the first asymmetric carbon atom. So, in here also this is your first asymmetric carbon atom. So, let's understand it on base of glyceraldehyde. So, you can see this is an asymmetric carbon atom. So, this junction is actually a carbon atom which is present here. So, you have an aldehyde on the top, you have hydrogen here, hydroxyl here and an alcohol here. So, this is an asymmetric carbon atom. Asymmetric means all the 4 substituents attached to it are different. Okay. So, now you can see this is plus glyceraldehyde, this is dextrorotatory and minus stands for levorotatory. Now, how can you tell whether it is D or L? So, as you can see, the hydroxyl group is attached to the right of the carbon atom, then it is called as D form, and if the hydroxyl group is attached to the left part or left side, it is called as L form. So I hope it is clear. So don't get confused with D, L and plus minus. Plus stands for dextro, minus stands for levo. D stands for the carbon atom is having the hydroxyl group towards the right. Then it is D, and if it's towards the left, it is L. Clear? Now let's see. All those compounds which can be chemically correlated to plus isomer of glyceraldehyde are said to have D configuration, whereas those which can be correlated to minus isomer of glyceraldehyde are supposed to have L configuration. For assigning the configuration of monosaccharide, it's the lowest asymmetric carbon has to be chosen. So let's take, this is the structure of glucose that we have studied now. Which is the lowest asymmetric carbon atom? This will be the lowest asymmetric carbon atom, right? So you have this much big group here. You have an hydroxyl group, hydrogen, and the alcohol group is present. So all the four are different, right? So this is your first asymmetric carbon atom. So the lowest first asymmetric carbon you have to take. So the lowest one is this one. Now we have to see on the right side you are having the hydroxyl group. So this will be D form, right? So this is D plus glucose. So glucose will be always plus. It is going to be dextrorotatory. So there won't be minus sign there. It will be always plus. So now that is about the structure of glucose, and I hope you are clear with how to identify D. Right. Now let's see the same one, CHO, and you have OH, H, H, OH, then you have OH, H, then you have OH, H, and CH2OH. So this is also another structure of glucose, another anomer of glucose. So here what you can observe, which is again the lowest asymmetric carbon atom, this one, right? This one will be the lowest asymmetric carbon atom. So here you can see the hydroxyl group is attached to the left of the carbon atom. So this is going to be L form. So I hope it is clear, right? So this is how you are going to identify whether it is D or L. So in the next session, we are going to see the cyclic structure of glucose, which is also very important. So I hope the basic structure of glucose and regarding carbohydrates and what and all topics we have discussed in this session is clear. So that's all for today. Thank you.